Hi students, I am Sheeba from Emmanuel Arsar JJ College of Engineering. Today we are learn about the topic non-ideal current voltage effects. Basically, most transistors have three regions of operation. Most transistor means metal oxide semiconductor transistors. First region is cut-off or subthreshold region. Second one linear or non-saturation region. Third one saturation region. In cut-off or subthreshold region where VGS less than VT. VGS means gate source voltage and VT means threshold voltage. In this, the drain source current equal to 0. In linear or non-saturation region where VDS less than VD set, IDS is equal to beta into VGS minus VT minus VDS by 2 into VDS. In saturation region where VDS greater than VD set, IDS is equal to beta by 2 into VGS minus VT the whole square. In all above equations, many practical effects are neglected. Practically, in linear and saturation region, the saturation current increases less than increasing VGS because of velocity saturation and mobility retardation. Next figure shows the ideal and simulated NMOS current and voltage plot. The green line shows the ideal plot and the blue line shows the simulated plot. Next figure shows the on and off current. First plot shows the on current. I on equal to IDS. It is on current is equal to drain source current in saturation region. In this, VGS is equal to VDS is equal to VDD. That is, when the voltage is increases, the current is also increases. In off region, I of equal to IDS in this cutoff region. In cutoff region, VGS is equal to 0, VDS is equal to VDD. When the voltage increases up to sub-threshold region, the current decreases and then the current increases to saturation region. Next is mobility retardation. Mobility retardation means strong vertical electrical fields due to large VGS cause the carriers to scatter and reduces the carrier mobility mu. This phenomena is called mobility retardation. The mobility retardation can be modeled by replacing mu with a smaller mu efficient. High effectively reduces mobility collisions with outside interface. Next is the formula for mobility efficient. Next one is velocity retardation. Next one is velocity saturation. Ideally, carrier tripped velocity and current increases linearly with the lateral electric field between source and drain. Tripped velocity rolls off due to carrier scattering and saturates of V saturation. E saturation is determined by expression V sat is equal to mu into E sat. For electrons, V sat is equal to 6 minus 10 into 10 power 6 centimeter. For coals, V sat is equal to 4 minus 8 into 10 power 6 centimeter per seconds. A plot of carrier velocity versus electric field is shown in figure. If transistor is completely velocity saturated, V equal to V saturation, then saturation current expression is modified to IDS is equal to C0 into W, VGS minus VT into V saturation. The low field mobility of holes is much lower than that of electrons, so PMOS transistors experience less velocity saturation than NMOS for given VDD. Therefore, value of alpha is larger for PMOS than NMOS transistors. Figure shows the velocity saturation current voltage effects. Ideal transistor on current increases with VDD square. IDS is equal to mu C X W by L VGS minus VT the whole square by 2 equal to beta by 2 into VGS minus VT the whole square. Velocity saturated on current increases with VDD. IDS is equal to C06 W into VGS minus VT into VG max. Our real translators are partially velocity saturated. Approximate with the alpha power law model, IDS approximately VDD the whole power alpha. I less than alpha less than 2 determined empirically 1.3 for 65 nanometer. Next we can see the channel length modulation. For a transistor in saturation, IDS is independent of VDS. This makes transistor a perfect current source. The reverse biased PN junction between drain and body forms a depletion region with a width that increases with reverse biased voltage. The depletion region effectively shortens the channel length to L efficiency is equal to L minus LD. The shorter channel length results in higher current IDS, increases with VDS in saturation region. IDS in saturation region is given by IDS is equal to beta by 2 into VGS minus VT the whole square into 1 plus lambda V into DS, where lambda is channel length modulation factor. As the channel length gets shorter, the effect of channel length modulation becomes more efficient. The lambda is inversely proportional to channel length. The channel length modulation model is useful for conceptual understanding of device. The channel length modulation is an important parameter for analog designer as it greatly affects gain of amplifier. Next is threshold voltage effects. When VT is VGS, for which the channel starts to inversion. Ideal models assumed threshold voltage is constant. Really depends on almost everything else. First one, body voltage, that is body effect. Second one, drain voltage, that is drain induced barrier lowering. Third one, channel length, short channel length. Next is body effect. CMOS devices consists of common substrate. The substrate bias level is normally equal, consider two NMOS transistors connected vertically in series. The source to substrate voltage are absorbed vertically upward. VSP equal to SP1 equal to 0 and VSP2 not equal to 0. It means VSP2 and VSP1 are not same. This variation of VSP causes variation in threshold voltages. That is, this variation of threshold voltage due to source to substrate voltage is referred as body effect. VSP affects the charge required to invert the channel. That is, increasing Vs or decreasing Vb increases Vt. The equation for threshold voltage is equal to Vt0 plus gamma into root of pi s plus VSP minus root of pi s. Pi s is equal to surface potential at threshold. Pi s is equal to 2Vt ln Na by Ni. It depends on doping level Na and intrinsic carrier concentration Ni. Gamma equal to body effect coefficient. Gamma equal to T0x by epsilon 0x root of 2q epsilon Si into Na equal to root of 2q epsilon Si into Na by C06. Next, for small source to body voltage in linear saturation, Vt equal to Vt0 plus k gamma into Vsp. Next is the equation for k gamma. Next is short channel effect. In small transistors, source and drain depletion regions extend into the channel, impedes the amount of charge required to invert the channel, and thus makes Vt a function of channel length. Short channel effect, Vt increases with L. Some processes exhibit a reverse short channel effect in which Vt decreases with length. Thank you.